Assalamualaikum and good morning to Dr. NURHANANI and fellow friends. Today, I want to present about Chapter 14, Multiple Linear Regression. My name is Haikal di Azman. My MATRIC number is D2020109259. Introduction. Multiple linear regression is the linear relations between two or more independent variables, x, and a single dependent variable, y. From this picture, we can know independent variable is religiosity and sense of coherence, and dependent variable is life effectiveness. We focus on these key elements. First, finding the multiple regression equation to the values of the adjusted R square and the p-value as measures of how well the multiple regression equations fits the sample data. Multiple regression equation and line. Multiple regression equation given a collection of sample data with several many explanatory variables. The regression equation that algebraically describes the relationship between the response variable y and two or more explanatory variables x. Like this. We are using more than one explanatory variable to predict a response variable. Now, in practice, you need large amounts of data to use several predictor variables guideline. Your sample size should be 10 times larger than the number of x variables. Multiple regression line, the graph of the multiple regression equation. These multiple regression lines still fit the sample point best according to the least squares property. Visualization. Multiple scatter plots of each pair x, y of quantitative data can still be helpful in determining whether there is a relationship between two variables. These scatter plots can be created one at a time. However, it is common to visualize all the pairs of variables within one plot. This is often called a pairs plot, pairwise scatter plot, or scatter plot matrix. Requirement for regression and formulas for BINTI. Requirements for regression. First, the sample data is a random sample of quantitative data. Each of the pairs of data, x, y, has a bivariate normal distribution. Recall this definition. Random errors associated with the regression equation are independent and normally distribute with a mean of 0 and a standard deviation. Formulas for BINTI. Statistical software will be used to calculate the individual coefficient, estimate BINTI. Selecting the best multiple regression equation for predictions. Use common sense and practical consideration to include or exclude variables. Consider the p-value for the test of overall model significance. Hypothesis HO B1 equal B2 equal BK equal 0. H1 at least 1 beta K not equal 0. Test statistic F equal MS regression divided by MS error. This will result in an ANOVA table with a p-value that expresses the overall statistical significance of the model. Selecting the best multiple regression equation for prediction. 3. Consider equation with high adjusted R square values. R is the multiple correlation coefficient that describes the correlation between the observed y values and the predicted y values. R square is the multiple coefficient of determination and measures how well the multiple regression equation fits the sample data problems. This measure of model fitness increases as more variables are included until it can usually reach normal or only by a very little amount. No matter how significant the most recently added predictor variable may be adjusted. R square is the multiple coefficient of determination that is modified to account for the number of variables in the model and sample size. 4. Consider equation with the fewest number of predictor variables if models that are being compared are nearly equivalent in terms of significance and fit value adjusted R square. This is known as the law of parsimony. We are looking for the simplest yet most informative model. Individual t-tests of particular regression parameters may help select the correct model and eliminate insignificant explanatory variables. Complete multiple regression analysis. Identify the response and potential explanatory variables by constructing a scatter plot matrix. Create a multiple regression model. Perform the appropriate test of the following: overall model significance, the ANOVA, the f-test, individual variable significant t-test. In addition, find the following: find the adjusted R square value to assess the predictive power of the model. Perform a residual analysis to verify the requirement for linear regression have been satisfied. Construct a residual plot and verify that there is no pattern, and also verify that the residual plot does not become thicker or thinner. Examples are shown below. Use a histogram normal quantile plot or Shapiro wheel test of normality to confirm that the values of the residual have a distribution that is approximately normal quantile plot, aka QQ plot, Shapiro wheel normality test. This will help you assess the normality of a given set of data. In this case, the normality of the residual when the visual explanation of the QQ plot and or the histogram of the data seem unclear to you and leave you stumped. Hypothesis: HO, the data comes from a normal distribution. H1, the data does not appear to come from a normal distribution. Alright, this is example for normal. Normal histogram of IQ scores is close to being bell-shaped, suggests that the IQ scores are from a normal distribution. The normal quantile plot shows points that are reasonably close to a straight line pattern. It is safe to assume that these IQ scores are from a normally distributed population. Next is example for uniform histogram of data having a uniform distribution. The corresponding normal quantile plot suggests that the points are not normally distributed because the points show a systematic pattern that is not a straight line pattern. These sample values are not from a population having a normal distribution. Skewed histogram of the amount of rainfall in Boston for every Monday during 1 year. The shape of the histogram is skewed, not bell-shaped. The corresponding normal quantile plot shows points that are one or at all close to a straight line pattern. These rainfall amounts are not from a population having a normal distribution. Heights of mothers, fathers, and daughters. The table to the right includes a random sample of heights of mothers, fathers, and their daughters based on data from the National Health and Nutrition Examination. Find the multiple regression equation issue, is which the response y variables is the height of daughter and the predictor x variables are the height of the mother and height of the father. From the display, we see that the multiple regression equation is daughter equals 7.5 plus 0.707 mother plus 0.164 father. We could write this equation as y equals 7.5 plus 0.707 x1 plus 0.164 x2, where y is the predicted height of a daughter, x1 is the height of the mother, and x2 is the height of the father. The preceding technology display shows the adjusted coefficient of determination as R minus SQ equals 63.7%. When we compare this multiple regression equation to others, it is better to use the adjusted R square of 63.7%. Based on StatCrunch, the p-value is less than 0.001, indicating that the multiple regression equation has good overall significance and is usable for predictions. That is, it makes sense to predict the heights of daughters based on heights of mothers and fathers. The p-value results from a test of the null hypothesis that beta 1 equal beta 2 equals 0, and rejection of this hypothesis indicates that the equation is effective in predicting the heights of daughters. Example of predicting height from footprint evidence. Dataset 2 in Appendix B includes the age, foot length, the shoe print length, shoe size, and height for each of 40 different subjects. Using those sample data, find the regression equation that is the best for predicting height. The table on the next slide includes key results from the combinations of the 5 predictor variables. For age, foot length, shoe print, shoe size, foot length, shoe print. This is the result. Using critical thinking and statistical analysis, delete the variable age, delete the variable shoe size because it is really a round form of foot length. For the remaining variables of foot length and shoe print length, select foot length because it adjusted R square of 0.07014 is better than 0.652. 0 for shoe pin length. Although it appears that only foot length is best, we note that criminals usually wear shoes, so shoe pin lengths are likely to be found than foot lengths. Hence, the final regression equation only including foot length y equal beta 0 plus beta 1 x1, where beta 0 is the intercept, beta 1 is the coefficient corresponding to x1 variable foot length. Caution: the methods of the above section, multiple regression, rely on variables that are continuous in nature. Many times we are interested in dichotomous or binary variables. These variables have only two possible categorical outcomes, such as male or female, success or failure, dead or alive, and etc. Indicator of dummy variables are artificial variables that can be used to specify the categories of the binary variable, such as 0 equal male or 1 equal female. If an indicator variable is included in the regression model as a predictor or explanatory variable, the methods we have are appropriate. However, can we handle a situation when the variable we are trying to predict is categorical and or binary? Notice that this is different situation, but yes. Using a dummy variable, the data in the table also includes the dummy variable of sex, coded as 0 equal female and 1 equal male. Given that a mother is 62 inch tall and a father is 69 inch tall, find the regression equation and use it to predict the height of a daughter and a son. Using technology, we get the regression equation: height of child equal 25.6 plus 0.377, height of mother plus 0.195, height of father, plus 4.15 of sex. We substitute in 0 for the sex variable, 63 for the mother, and 69 for the father, and predict the daughter will be 62.8 inch tall. We substitute in 1 for the sex variable, 63 for the mother, and 69 for the father, and predict the son will be 67 inch tall. That's all from me. Thank you.